Welcome to episode 123, Spotlight, Software, Firmware, and Information Integrity, focusing on Control S-7. Integrity is what ensures that code, firmware, and data behave exactly as intended, no more and no less. Without it, systems may run the right software but for the wrong reasons, guided by hidden changes or malicious insertions. Integrity protection keeps digital trust anchored, confirming that what executes, boots, or stores information remains untampered from source to runtime. When properly managed, these controls make modification visible, unauthorized change reversible, and restoration predictable. Integrity is not just a feature, it is the quiet foundation of reliability. Building on that foundation, integrity begins with signed updates and strong provenance checks for every code and configuration package entering the environment. Signed updates use cryptographic signatures to prove origin and prevent unauthorized alteration. Provenance ensures that what is deployed truly comes from a trusted creator, repository, or vendor. For example, operating system patches should verify digital signatures before installation, rejecting unsigned or mismatched packages automatically. In distributed environments, provenance extends to verifying checksum manifests or package metadata at each hop. This continuous chain of authenticity makes every update traceable back to its rightful source, closing one of the most common attack doors in modern infrastructure. From there, boot integrity and measured startup processes verify that systems begin in a known, trusted state before loading higher-level components. Secure boot ensures only signed firmware and bootloaders initialize hardware, while measured boot records cryptographic hashes of each stage for attestation. For instance, a workstation with a trusted platform module can confirm during power-on that its firmware, kernel, and drivers match approved baselines. If even one element deviates, the system halts or alerts before exposure spreads. Boot integrity transforms startup from assumption into verification, proving that trust exists because it was checked, not because it was hoped for. Protecting firmware update pathways requires equally tight control, since firmware operates beneath most security tools and can outlast operating systems. Update mechanisms should enforce authentication, encryption, and strict version validation. For example, network equipment should accept firmware only when signed by the manufacturer, and the device should record the update event immutably. Unauthorized firmware updates represent one of the most dangerous compromises because they persist invisibly. Securing these pathways ensures that only deliberate, approved updates reach the device level. Integrity at the firmware layer anchors confidence for everything stacked above it. Application Allow listing defines which executables, scripts, and libraries are permitted to run and in what contexts. Rather than blocking known bad code, Allow listing enforces a default deny stance for execution. Policies should specify both approved applications and their trusted publishers, reducing risk from unauthorized binaries. For example, an organization might allow only signed internal tools and vendor software verified against a manifest. Scope management prevents allow lists from becoming too permissive or impossible to maintain. When aligned with operational patterns, allow listing creates predictable runtime behavior, a form of living integrity enforcement that operates continuously across user and system boundaries. For data itself, hashing and digital signatures ensure that what is stored or transmitted remains authentic and unchanged. A hash acts like a fingerprint. If even one bit differs, verification fails. Signatures bind that fingerprint to a trusted entity, proving authorship and origin. For example, an electronic medical record system can hash patient files daily and verify them against known baselines to detect corruption or tampering. Using multiple independent algorithms reduces risk of collision. Data integrity controls complement software verification, extending authenticity from executable code to the information it processes and protects. Detecting unauthorized modifications promptly closes the loop between monitoring and integrity assurance. Systems should alert when protected files, configurations, or binaries change unexpectedly. File integrity monitoring tools, system logs, and checksum comparisons provide continuous visibility. For instance, detecting an unauthorized edit to a database configuration might indicate privilege escalation or lateral movement. Early detection minimizes damage by enabling immediate containment. Timeliness is everything. Integrity controls are most valuable not just when they detect tampering, but when they do so fast enough to stop propagation and enable controlled restoration. Once an anomaly appears, compromised components must be quarantined, investigated, and restored to verified clean states. Quarantine isolates affected systems or files to prevent spread, while forensic analysis determines root cause. Recovery relies on trusted backups or golden images with validated signatures. For example, if a firmware integrity check fails, the device should switch automatically to a previous verified version. This containment mindset ensures that corruption does not cascade across interdependent systems. Treating restoration as an integral step in integrity management transforms failure from crisis into practiced recovery. Segregation of duties for signing and deployment prevents internal compromise and preserves confidence in validation results. The team or system that signs updates should never be the same entity that deploys them into production. This separation requires deliberate process. One group validates authenticity, another installs, and audit teams verify the record. For example, a build pipeline may produce signed packages using a secure key vault accessible only to release engineers, while operations staff deploy them. Dividing these powers limits insider risk and enforces collective accountability. Trust thrives when no single hand holds every key. Maintaining attestation logs and associated artifacts creates a durable record of integrity decisions. These logs store measurements from secure boot, hash verifications, and signature validations. Artifacts, such as signed manifests or attestation tokens, provide proof during audits or investigations. For instance, cloud instances might generate attestation reports during startup that confirm verified firmware and operating system images. Preserving these records makes integrity evidence verifiable and repeatable. When questions arise about when a system last booted clean or which version was installed, these logs transform conjecture into certainty. Documentation is both evidence and confidence. Exceptions, when unavoidable, must be time-bound and counterbalanced by additional controls. A legacy device lacking signed firmware may continue temporarily under heightened monitoring, isolation, or frequent checksum verification. Every exception requires justification, compensating measures, and an expiration date. Without these constraints, exceptions drift into silent vulnerabilities. Transparency about deviations ensures they remain temporary bridges rather than enduring cracks in the program. Integrity cannot coexist with indefinite exceptions. It survives through controlled deviation managed with discipline. Metrics then quantify performance through tamper detection counts, restoration times, and verification coverage. Tamper attempt metrics show how often controls engage. Restoration time tracks how quickly systems return to validated states. And coverage measures how much infrastructure participates in attestation. For example, reducing average restoration from 8 hours to 2 reflects operational maturity. Metrics highlight strengths and expose neglected areas, guiding future investment in monitoring and automation. Numbers convert technical confidence into managerial assurance. When integrity performance improves measurably, the organization proves that protection is active, not assumed. In conclusion, Control SI defines layered integrity as a chain of verifiable proofs spanning code, firmware, and data. Each link, signing, measurement, monitoring, and restoration, reinforces the others. True assurance arises not from blind trust, but from evidence that each component remains as intended. By enforcing cryptographic validation, disciplined process, and clear accountability, organizations keep systems predictable even in a world that changes constantly. Integrity, when treated as a living practice, becomes the heartbeat of trustworthy technology, steady, measurable, and dependable under every condition. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.